8:15 on my clock. Shall we start it off? Shall we go live? Let's put our
Yeah,
faces on the internet.
we can get going. We're doing good, Ethan. And how long are we going to be streaming from Classic? I think we're aiming for about an hour,
Whoa,
maybe a
whoa,
little bit
whoa,
less
whoa, whoa.
today.
This is a relatively basic live stream. We're shooting for about 30 minutes plus or minus 10.
30 minutes. Okay, Classic. We're going 30 minutes here.
This is going to be a relative quickie.
Do it. All right.
So, George, how's it
Sounds
going? I
good.
haven't seen you at work today.
Oh, were you at work today?
Were
I
you
took the day
not?
off.
Oh my God.
I needed a B day.
Well, good
A
for
B
you.
day where I got to go on a trip to Lowe's and buy myself a new tool.
That's not a bad day.
This this is the struggles of having a full-time job apart from the maker life, as you know and as many other people know at this point.
The
Oh,
side hustle slash hobby just always
the side
intruding into
hustle.
your life. That's a good
It,
thing.
and for me it always will be. I'm not really planning to move on from that, but I like it, and it'll give me a lot more gray hairs in the long run, but I'll take it.
You'll feel more accomplished though at the end.
Yeah, yeah. After many 1 a.m. nights and starts to.
Builds
How
character
about you?
then.
How was work today? Well,
Work was
yeah, lots of
really
character.
boring. Um, Honestly, I really didn't want to go into work because last night I thought I destroyed the circuit in my garage. So I was like all emotionally prepared to like
Oh
call
yeah.
up an electrician this morning and be like, all right, I'm not leaving my house until I get power back to my CNCs. And then someone
Yeah.
on Instagram tipped me off to the fact that circuits can be paired with GFCIs in other rooms. So I started looking around the
Oh
house. I
yeah.
looked in the bathroom, and that circuit had been tripped. And so that is what was killing power to the garage and also to the exterior circuits in the house. So the electrician, when he
The
wired up the
exterior ones
house,
too.
he just threw a bunch of different rooms and outlets onto the same circuit, which kind of annoying. But
Yeah.
we're good now. I didn't have to spend any money. Um, but because of that, I was all
Ah,
like
that's a good. It's a good
angry and
day.
like frustrated at 11 p.m. last night, and I was I'm just not gonna go into work. And I was all ready to like get this knocked out by like noon, and then just spend the rest of the afternoon machining. But no, I went into work, unfortunately. Oh
Yeah,
well.
you bit the bullet and went in.
Yeah.
For
All right.
me, I was planning to actually go to work, and then I woke up. I'm like, it's Fourth of July week. Almost everybody else is taking off today, and I can get some stuff done. I'm planning to go to the beach this weekend and not get a lot of work done, unfortunately. So maybe I'll do some today.
Nice. All right. So
Yeah.
what do you say we start rolling into this?
Yeah, let's get this 30-minute timeline for you get going here.
All right, guys.
Let's see
So
what we
here
got.
is the 30-second background. I had a guy reach out to me on um, through email about how to make a really simple part. He makes like wooden tops and stuff, and he was looking to cut out the profile of a top and make some holes for insetting like stones and other ornamentation. And he's a beginner fusion guy. Um, and so going from a basic design, he has a bit of CAD practice. Going into the cam side of it, he wasn't really sure how to get started. So I'm going to make a part that looks somewhat similar to what he had, and I'm going to take you from basically start to finish of the cam process. But before we do that, let's first start with just let me walk you through what the part is. Um, so first we start with the sketch, 2.5 inches in diameter for the body. Um, Extrude that out to, I think it's half an inch, 0.375, 3/8 of an inch. And then we have the little um, stem here where we would stick in like a little handle for a top. It's a little thicker. So the overall part thickness is half an inch from top to bottom. And I just did a radial pattern of holes around the outside, um, different sizes. One of them is a 0.125, so basically 1/8, with no room to spiral or ramp in for a contour, and the other one is a little larger at 0.2 inches. And so I'll go over a couple
How
different
about the
strategies.
middle one?
Middle one I think is 3/8.
All
Yeah,
right, so you got a
so
bunch of different
we'll go over a
sizes.
couple different strategies you can use to just punch some holes in this thing, based on the 2D toolpaths you have available to you.
What's up, RWT? Can you make your cursor highlight so it's easier to see what you're clicking on? I don't know if we're able to do that live, but maybe for the next one we could add that in.
Does the cursor not? Oh, the cursor is really tiny, which is the problem. Next time I'll
It
change
is
my
kind of tiny,
resolution to
yeah.
1080. Um, I'll just I'll try and be a little more verbose about what I'm doing to compensate. I do occasionally
And
answer
then,
simple
yeah.
fusion questions on Instagram. It's kind of tough to give a more long form answer though. But if you DM me, I'll try my best. Otherwise, I'm gonna sick you on Lars Christensen or something. All right, so
Shoot you to the guys.
we have our basic part, 2.5 inches in diameter, half an inch tall. So we're gonna go into the cam window. Um, Before you do anything, you need to make sure that you have some tools loaded up. So there are sample tools in Fusion, which is just a gigantic library of drills and generic end mills, which you can pull from. But I like to create my own little set of tools. Here I've got a list of tools from Carbide 3D that I can draw from and use. And you need to have tools to create a toolpath. So this is sort of the prerequisite. If you're just rolling into it from, like, let's say this is your very first Fusion 360 cam part. I've got a video on my channel. I think it might be the second. I'll link it in the description later.
I think it's one of your second ones, yeah.
But basically of how you add a custom tool into Fusion 360. So assuming you've got tools,
And these are pretty general, right? They
yeah,
don't have to
like
be like the specific tool you bought off eBay or anything
yeah.
like
So
that.
I'll
It's
just open
just
up one of these tools, basically name it whatever you want, and just the cutting parameters. It's a
exactly.
flat end mill. You say it's got 2 flutes or 3 flutes. What's the diameter? How long is it? How long are the flutes? And that's really all you need. The feeds and speeds
Yeah, and whenever
tab.
you buy it, that stuff's easily on the label right there. It's just right there for you.
Yeah, like you should know all this information before it arrives. Um,
Exactly. Yeah.
in the feeds and speeds tab, you can tell it a nominal like spindle speed or feed rate, but you're always going to custom tailor that just or tweak it based on what you're cutting. So I mean, I've got a library of standard carbide end mills, but I use them in aluminum, I use them in wood, I use them in plastic, and every single time these feed rates are going to change. Um, Thank you, Kyle. All right, so we've got tools, and you need to create a setup. So a setup tells Fusion, hey, how big is the stock material you're cutting from going to be? So you create a setup. Um, the first tab is the setup tab, and you can say which way is up. So right now, if you can see the blue arrow, it's facing up, and that's just based on the default orientation of how I modeled this part. And you can change this depending on like, oh, hey, I accidentally modeled it sideways. I need a different axis to be Z positive. But here, in my case, I want the blue arrow, Z axis, to be up. If it's not set correctly, you can go into select Z axis and X axis, or just basically you can pick any two orthogonal axes to establish a coordinate system. But it's just easiest if you model the part upright in the orientation you're going to cut. And then the most important one, which I know you've screwed up, George, is the stock point. So that tells you where the 0 point is. So if you're going to zero your CNC by touching the end mill down on the top of the stock, then you want your origin to be at the top of the stock material. If you're like me and I've often been touching off on the wasteboard, I actually want the origin to be at the wasteboard, so that establishes my zero. So it sort of depends on what you want to do, but you should know where the origin, uh, where Fusion thinks your origin is. Top of the part, bottom of the part,
And the
or
way,
some awkward combination of the two.
yeah, and the way you know you're gonna screw this up, if you're screwing this up, just from my own very recent experience, when you're actually cutting, if you're realizing that the z-axis is actually way off compared to where it's supposed to be, if it's trying to retract way more or go way past the board, it might be because of this that you just set the origin wrong when you generate the G code. And simple as that, made a nice couple mistakes this week, but quick fixes and then you get it up and running again.
Yeah, so that's what's important to remember in the setup tab. Next up is the stock tab, and here you can basically say that yellow volume, how it encompasses the part. If you tell Fusion that, hey, I'm starting with 0.6 inch thick material and my part's only 0.5 inches tall, well, then there's an extra 0.1 inches of material above the part that you want to take into account. But for the purposes of this academic exercise, we're going to say that we have exactly 5-inch thick stock. So I'm going to say no additional stock. And so that is our bounding volume of where Fusion can operate. So we'll hit OK, close out the setup window, and I think the first order of business is to clear out the material around our central shaft. So this blue face. We have to sort of pocket that out, bring the face of the material down so that we don't have extra material left over after we drill all these holes. And there's a couple ways you could do that. You could just drop a 3D toolpath on the part, which 3D toolpaths are model aware. So you can sort of just say, hey, I'm going to use a 1/4 inch flat end mill and just hit OK. And it'll automatically just cut away all the part and all the other material around your stock. But that's sort of a fire and forget, not very surgical approach. What I prefer to do for something like this is to apply a pocketing toolpath. Pick an end mill. We're going to go with a 1/4 inch. We're going to say our geometry. Our pocket selection is this top face. Highlight that. And then I like to just first hit OK, see what the toolpath spits out. We're going to go through the cutting parameters a little more in depth for some of the pocketing operations for the holes. But for now, I just want to show you how you can select a face and machine away only what you want. So right now, we've got a toolpath that goes around the main stem, takes out the top face. I'm going to simulate it to show you what it looks like. Put on the stock. So it's going to go through and take out most of the material there. But you'll notice that this toolpath doesn't touch the surface completely. And that's because there is stock to leave selected. So if you disable that, it'll actually go all the way down to the surface of the part. All right, so I know I hand waved over a lot of that, but this was sort of just one of the first operations just to get it out of the way. Let's do a 2D pocket to take out some of these larger holes. We're going to use an 1/8 inch end mill. So I'm going to go into my Carbide 3D tool library, pick out an 1/8 inch flat end mill. Yeah, simulation is an awesome feature.
Yeah,
and it's
fantastic.
depending on the complexity of your part, sometimes it'll also show you part collisions. So you'll see like a gash across your part, and when you simulate it, it's like, oh, that's because the end mill decided to go from point A to point B, and it didn't realize that part of your model is sticking out in the middle of the way or something. All right, so 1/8 inch end mill.
Yeah, it's the best way to visualize what the computer's actually thinking when it's giving you that G code there. If you guys have questions, by the way, go ahead and shoot them out there while you're watching. We'll try to answer as we go along.
All right, so I know that my resolution's a little tiny, so I'm just gonna walk through this step by step. So I have an 1/8 inch flat end mill selected. Um, no need for coolant. Even if you have it enabled, it's not going to do anything because the Shapeoko doesn't have flood coolant. Spindle speed doesn't matter. You're setting it manually when you turn on the router. But for some of the cutting parameters, it can tell you like, hey, I have a surface speed of 600 SFM driven by the fact that my RPM is something or other. It's a nice thing to know in the back of your head, but it doesn't affect anything at this point in time. So for materials like wood in an 1/8 inch end mill, I like to go about 60 inches per minute. It's just a good starting point. You can always override that. The lead-in feed rate, I usually do about, if I'm being conservative, about half of my cutting feed rate, otherwise about 10 to 20 inches per minute backed off from the cutting feed rate. So I'm going to put in 40 for lead in, lead out, 30 for ramp, 20 for plunge. And you'll see when I simulate this how each of those values affects how the end mill moves. So that's it for the tool tab. Second tab is the geometry tab, and that's going to be where we select these holes. So in the pocket selection, so hard maple.
Hey,
if you're
before
on
you go on, yeah, you see the hard maple?
Yeah. So there are sort of two ways you can go about adjusting for a denser material. One is you could back off on feed rate or back off on depth of cut, or you could increase RPM. If you're cutting on a Nomad, you're kind of stuck at 10,000 RPM max. But with the Shapeoko, you can just dial back the feed rate, crank up the spindle speed, and just sort of find a place where you can sort of just listen that it's not chattering or struggling too hard. You can also just look at Carbide 3D's like sort of their suggested feeds and speeds, but a lot of what I've done is just over time I develop a gut feeling, and I start around 60 for 1/8 inch end mills, I start around 90 for 1/4 inch end mills, and you just cut by ear and you figure it out as you go. It's not too critical as long as you're not
online, right?
burning the wood. You should be fine. All right, geometry.
Online, you can find a whole bunch of like calculators for
There,
this too, right? With
there
the
are
different
some.
cutting.
I
don't know how trustworthy they are, but I mean,
like some of them, like for like a shop bot, it's going to be different than a Shapeoko because of like rigidity and how fast they move. But you can always use them as a starting point and back off if something gets a little too hairy. Anyway, geometry, pocket selection, that's where you select the contours or the edges or the faces of what you want to machine. So my 1/8 inch pockets, they don't go all the way through. So I can select that face or I can select that contour. But for the big holes, you have to select the edge because there's no face for you to click on. So I'm going to select the edge there. I'm going to select all 6 of the medium-sized holes.
That's some impressive selections there through the top of the part. I always have to flip it around to get to the damn sides.
That's because you're probably not a PC gamer. I've got those mouse skills.
I am not a PC gamer.
So once you have this selected, that's basically all you need for the geometry tab. For the heights tab, this is where you can establish how far the end mill retracts when it moves or when it pulls out of the part, or when it starts, instead of rapiding into the part, it slows down to a more conservative feed rate. And I'm going to leave these default for now, and I'll show you how you can sort of optimize your tool travel later. So for the passes tab, this is where you really have a lot more control than any other 2D CAM programs like Carbide Create. So I'm going to uncheck stock to leave for now, but I will do multiple depths. So this means instead of your end mill plunging all the way to the bottom and then drawing a circle, we're going to step down in more conservative increments. So I'm going to do 1/16 of an inch, 0.0625 maximum roughing step down. I'm going to do even step downs, just so that they're sort of evenly distributed.
Have you ever seen a situation where you didn't use the multiple depths and just like plunge right? I've always been curious with that one there.
So there was a
Like I
part I
don't know
did
when.
today with a very soft material, or if you're doing a finishing pass where you can do the full depth of cut, but
A
that's usually
finishing
after
pass.
the majority
Yeah,
of the
that
material's
obviously
been
makes sense.
removed.
You're right.
Um,
Yeah. Okay. That makes sense.
Last tab is for linking, and that's sort of just some nice little additional movements that the CNC does to sort of ease its entry and exit from a part. I'm not going to touch them yet. I'm just going to hit OK. We're going to see what the toolpath looks like, and I'll explain how you can optimize some of this stuff later. I guess I do have to optimize it now. So I'm getting an error that's saying what or more pockets were not machined because they're too small to be reached with the given ramping constraints. So I'm going to go in, back to the linking tab, and sort of explain that lead in and lead out is, I'll explain that later actually. So ramping is basically the end mill easing its way into the material. Without this, how basically Carbide Create or Easel, how they set up their moves is they'll see a contour, they'll move to the edge of the contour, shove the end mill straight into the material, and get going. And that looks like this. So the end mill goes basically down into the part and just immediately starts following a contour. So from a different angle, straight plunge into the material, and then it starts moving laterally, which is fine for most materials, but in aluminum, or if you really, really care about accuracy, that's not the best way to go about it. And so there are different ways of sort of making it easier on the end mill, and one of them is the profile and the helix. So helix is what usually ends up happening, but the diameter here is set too large, so I'm going to make that really small, 0.05. So a little less than a 16th of an inch diameter helix. And so now what happens is the part, or the end mill, starts spiraling into the part before it starts cutting. So that's one way, but the way it's set up now, it's wasting a lot of time spiraling in. So one way to change that is to modify the top height. The top height is basically when your toolpath actually starts planning out its cut. Anywhere above the top height, it's really just moving up, moving laterally to a new position, plunging straight down. Top height is when ramping starts happening, when cutting starts happening. And so if I set my stock top to this top face, the end mill starts helixing in a lot closer to the part. And I can lower that margin even further by setting the ramp clearance height to something really small. I'm going to say 0.01 just to illustrate how close you can get it. And so now it's getting really close to the material before it starts moving. So if you're sure that this top face is clear, by all means, make the toolpath more efficient and bring the end mill all the way down to the part before you start machining. If I simulate both of these and go to the next operation, after we've cleared that top pocket, then it starts ramping in really close to the material and it makes that pocket.
That's pretty cool.
So that's...
We've got a question. I'm not too sure what it's actually asking. I might, maybe we'll ask them to rephrase it. Do you get what they're saying?
So I think what he means is you're seeing like basically horizontal striations or just marks as the cutter steps down. So the way you get around that or you improve that is you do a finishing pass. So what's happening is, let me make another. Let me do it as a contour up, just to demonstrate. So I'm going to do 0.1 inch step downs. So what's happening?
For those that are watching, the question is, where Classic is seeing cutting marks on his plane when he's cutting hard maple.
As the end mill is taking multiple step downs, each time it goes around, it's cutting slightly differently, and that's because of tool deflection. So
yeah,
if you imagine this cutter spinning in a clockwise direction, every time a tooth of that end mill comes around, it's sort of pushing itself off the edge of the material. So this end mill is actually not touching the part when it's cutting. It's actually offset like 1/1000th of an inch or 1/10 of an inch. But that's enough that you'll see just a little bit of fuzziness or a little burr between step downs. And so the best way to get around that is to take one final pass at full depth, sort of just a whisper cut or a spring pass, to clean up that last extra margin of material.
Yep. And I think I just realized his second question. I think what he's saying is he'd like to just program so that, say he tells it to cut an 1/8 hole and just put in a 1/4 inch end mill instead, so that he's just cutting double the area. But I don't know why we wouldn't just put that in the model at that point. I don't know. Do you see that second one there? Because
yeah, I'm not sure I'm entirely
it seems like
following.
Trying to do like double the work with. Yeah, if you could rephrase that second question, Classic, we can kind of get to it.
But I'll try and address
sure
a couple things.
Completely.
So if you're trying to do a finishing pass, like let's say you made this first cut around the part and you're getting marks and you want to clean them up, what I like to do is just duplicate, Control D or right click, duplicate a toolpath, go into it, go to the passes tab and just turn off multiple depths. So that way, the first operation cuts all the way down.
Yeah, that's great.
The second operation, it just comes in at the full depth of cut and sort of cleans up that wall.
That's a nifty trick. You create that pretty fast like that.
Yeah. You can also, to sort of enhance that, because sometimes that last spring pass or the whisper cut won't get everything, is to leave a little extra stock around it. Just like 4th thou up to 10th thou. And so what's going to happen is I'm going to zoom in from the top down. That first pass goes around, it leaves a little margin, and that second toolpath, if you look closely, is just a little further inside. And that,
look at that.
means when that comes around that it's cleaning up and exposing fresh material all at once. And what that looks like in the simulation, which run on the stock, is first pass and then second pass. Gotta pause it. So it's exposing just a little more material when it's coming around again.
I think that might actually answer his question from what it looks like. Cut the same spot twice, clean it up in another end mill. Same kind of concepts there, but let us know, Classic, if that kind of answers it for you. All right, so
technically where we should be is just finishing these first holes using a pocket operation. So pockets are one way to make a hole. Contours are another way. Contours are what I just used to cut around this part, but you can also just select the inner radius, and I'm going to turn off lead in. And it'll basically just trace the bottom part of the hole. You could, of course, do this in multiple step downs, which is much safer. Let's say 0.1, even step downs, whatever. This is just as an example. So you could come down and cut out a hole that way. Why you would use pocket versus contour in holes like this one, where your diameter is less than 2 times the diameter of your end mill, your end mill can come, walk around that hole, and not leave anything in the middle. If you were to contour the center hole, you would actually leave a little plug of material in the middle that could break loose, jam the cutter. A really small bit of stock that's left over isn't going to cause any issues, but
you never want like
yeah,
unexpected wood where you don't know it's going to be when you're cutting, right?
The fewer surprises you have, the better. And so in a case where your hole is larger than 2 times the diameter of your end mill, I'd rather use a pocket and methodically just clear out that hole completely. So instead of that contour, I would rather pocket out that entire hole. We'll do step downs of 0.07, no stock to leave, just run it. And
you could have also done a contour with tabs, right? I mean, that would be fine.
But holding...
But getting tabs in that little section in the middle.
Plus, that little nub, its footprint is very small, so it's very liable to tip over, be knocked over, and so it's just better not to tab that part.
Good point. Yeah, agreed.
So we've got holes about 2 times the diameter, down to 1 times the diameter. Holes above that, you can use contours, you can use pockets, it doesn't matter. For the smaller holes, I like contours just for efficiency's sake. For bigger pockets, use the pocketing operation just to make sure it's more complete. Or if it's like a massive pocket, then you could tab that little core in the middle that would be left behind. For these holes, 1/8-inch holes, you can't move laterally inside that hole because that's the same diameter as your end mill. So you could either get a smaller end mill, or you could use a drilling operation. Now, most people say you shouldn't use drilling operations.
Got a plane coming.
That is a motorcycle roaming our neighborhood.
That's a motorcycle? Wow, that's...
yeah.
Great.
Anyway, so most people say drilling operations don't work well in a CNC router because the RPMs are too high. You just get scorching on the walls. But for short drilling operations, it's pretty okay. That's how I made my DIY vacuum table. I just took a 1/16-inch end mill and just pecked out a bunch of holes. So for these 1/8-inch holes, I'd actually, especially in wood, I wouldn't do this in aluminum, but in wood you could totally get away with doing a peck drilling operation. So the way you use that is you select the tool. I have the 1/8-inch selected. RPM, you're not controlling that, or the router's in control of that, not Fusion. Plunge feed rate, pick something safe, 15 inches per minute. Retract can be pretty quick. We'll go like 45. And then...
And I don't know how many Maslow users there are out there, but this type of drilling operation is going to be, I think, even more useful for the Maslow users because you're able to cut away without pushing the router away from the plane. I'm going to be making a video about it on my YouTube channel. I don't want to get too much into it here, but this is one to pay attention to if that's your CNC of choice. So sorry, I'm keep going.
That's right. So if you select
you guys are hilarious.
the holes and you hit OK, your drilling operation is going to look something like this. Straight down, straight back out, and that should be okay. What's a safer way to do this is to peck drill it so that you retract the end mill at certain increments so that you can clear the flutes and make sure that you're not just grinding sawdust into the walls and causing friction and burning and terrible things like that. So the last tab in the drill operation is cycle type, and you can say something like chip breaking with partial retract, and that gives you a couple more options. And how that works is you can say, I'm going to peck in 0.05 inch increments. When I drill an accumulated depth, so I'm going to say 0.15 inches, it's going to retract out. Chip break distance is how far you're backing off each time. I'm going to do 0.03. I think that should be able to illustrate the point. And I'm going to simulate this. I'm going to turn off stock just so that you can see what's going on. So if you look closely, the demarcation of the flutes on the shank, you can see it's going down, it's coming back up, and it's going down. So from the beginning, down by 0.05, down by 0.1, down by 0.15, and then it retracts all the way. And so
That's pretty
doing
cool.
that, you can sort of guarantee success by making sure your flutes are cleared, and it's a lot less stress to do it this way than to just plunge the end mill all the way down, all the way back out. So that's my preferred way to drill out.
I'm definitely going to be using that. Definitely going to be using that in the future. That's pretty sick.
Oh, nice. You've got another Maslow user out there.
Yeah, we got a Maslow user in here, and his daughter. That's awesome. It's great to get, like the kids involved at a young age on this kind of stuff. I think it's just awesome. So he kind of re-asked a question. I don't know if you saw Classic. I think he wants, maybe even just he wants to offset his end mill so that he's cutting off less. Take a look at the question. Maybe I'm just not getting it, but
make a flat surface with a 1/4 inch end mill. It'll cut away a 1/4 inch at a time. I want to make it only cut half that at a time.
So like offset it, right? Come out from the
or
side.
Step downs.
Use half the end mill. I wonder. I think he said facing it, right? I want to make a flat surface.
It sounds like so. If we talk about that first operation, where I'm just taking the part down and building up that little core in the middle, I can change I can use multiple depths and say, instead of coming down 0.1 inches at a time, I can make really tiny passes. I can do 1/32 of an inch little cuts, so that each layer that I'm cutting is really low stress on the CNC. So I'm just coming down layer by layer, 0.03 inches at a time. You can change that step down to whatever you want until you feel comfortable that your machine can handle it.
Yeah.
And once I could do this with an 1/8 inch end mill. I could do this entire thing with an 1/8 inch end mill, so I don't have to change tools. If you're comfortable with tool changes, great. If not, just go slow and steady until you develop the workflow and the right checklist to make sure that you can do it properly. So I'm actually, if anyone else has any questions about specific toolpath parameters that they want to get a little more info on, just drop them in the chat. But I'm going to run through sort of like my nominal process of how I would tackle this piece, and
all right, let's
it might be a little fast. Some of the topics might be a little more advanced, but I just want you guys to have sort of an understanding of how to tackle this, or different ways.
Yeah, this will be recorded, so everybody can kind of play it back later.
Yeah, it's just good to get an understanding of like what are the possibilities, what are the variables you can play with, so that you know what questions to ask later. All right, so we've assumed that we face the part down to this level, so that's clear. When I'm doing this pocket, that's pretty well optimized. I'm going to do one thing different. I am going to use some stock to leave. 0.01 inches, nothing axially. I just want a little extra thickness on the walls, such that when I'm cutting, you can see the end mill is leaving just a little extra on the walls. I'm going to come back with a contour operation, I'm going to create a derived operation, 2D milling, 2D contour. And so basically, using the same tool, same geometry, it creates a 2D contour operation based on the previous one.
Yep.
I'm going to use multiple depths of about 0.1 inches because most of the material in these holes is gone. So I can come back, I can take a little more aggressive pass, and that's just going to clean up, with no stock to leave, the rest of the walls. So what it looks like is first the pocket, then that cleanup contour. And the two of them together should leave me with a pretty good tolerance hole. Because most CNC machines, they will, there's a little backlash, they will actually create like a smaller hole. So you got to come back with a really light cut that doesn't stress the machine, and the machine can just effortlessly move out to that outer boundary that it needs to cut.
Gotcha.
So initial pocket, hog out most of the material, contour the rest. And since I'm doing this contour as multiple step downs, how that's going to play out is when I simulate it, I'm going to turn off stock so you can see it. Go to contour operation. It's going to go down, go around, and step all the way down. If you didn't have keep tool down checked, it would retract in between each layer. So that's one way to sort of speed up the process. If any of you have drilled holes by watching the end mill go down, move around in a circle, go all the way back up, then go all the way back down, that's because you didn't have keep tool down checked. And so that saves a bunch of time while you're waiting for the Z-axis to move.
Oh my god. You just taught me that. Oh, that's sad. All right. Still a noob, that means. I'm still getting there. That's great. Could have should have kept that with myself.
Blue circles.
All right, anyways.
Oh. All right, I think I understand. Classic. So he's asking about
he
step
wants
over.
to come in.
So
yeah, he wants to step over at 1/8 intervals.
Computer's slowing down. So I'm going to change this back to, so let's say you start with this toolpath, and to bring your material down to this face, you're going to have a lot of like sort of concentric grooves in your part because your step over is really large. So sort of your cleanup, your finishing for that facing operation would be to, I just duplicated that pocket operation. I'm going to go in to the passes tab, and I'm going to change the maximum step over down to, I like about 60% of the tool diameter, so like 0.15. Or you could reduce it down to 1/8. So now you can see initial toolpath, follow-up toolpath to clean it up. Your step over is a lot smaller, and that should give you a much smoother finish on the top.
Yeah, I think that's exactly what he was looking for.
All right, so we've got medium-sized holes, sort of pocket to clear it out. We could actually do that as a contour. So you can see there are multiple step downs there. So to do that more efficiently, what I actually like to do, create a derived operation.
It's a lot of them.
2D contour. Whoops. I canceled that prematurely. 2D milling, 2D contour. No multiple depths. Ramping all the way down to the bottom. Let's go about 5 degrees. And what that's going to do is your end mill is going to spiral all the way down to the bottom of the part. It's not going to stop, do a layer, then step down again. It's going to spiral all the way down till it hits the bottom. It'll move in a circle just to make sure it's gotten everything, and then it'll retract. So it's one continuous motion. And that's the quickest way to contour a hole, assuming your diameter...
Does it do it? I'm assuming it does a full circle at the bottom, right?
Yes.
I mean, to clear it all off at the bottom. Yeah.
So it's spiraling in, hits the blue, and it does one complete circle, and then it steps back. So that's the smoothest way to make a hole.
For those who, you know, if you want to make sure you get through it, I guess, right? You could actually choose your plane for the bottom plane to be maybe the bottom of the stock, right, instead of the bottom of the model, so that you know you're getting through your part, and you cut through some of your wasteboard at that point. But that's to confirm. Oh, did we lose you? Because I'm full on the Skype here.
I was. What have you studied? I did my undergrad in mechanical engineering. We had almost no hands-on experience with CNC. We made our own G-code by hand once for a class project, and my teacher screwed it up. And I never touched a CNC until after I did grad school. So, engineer by training, but all of this actual digital fabrication stuff is self-taught. So what George was talking about is if you want to make sure that you cut all the way through your part, sometimes you leave an onion skin on the back, is you can go into the contour or pocketing operation, go to your heights, and normally your toolpath would end at the selected contour. So since I selected these bottom rings, it would stop there. I can say overshoot that by negative 0.03 inches, let's say. And now the toolpath shoots through the bottom a little extra. So you can use that to sort of guarantee a cut, or if you didn't cut through the first time, you just repost this G-code with that little tweak, and that'll make sure you get a clean cut all the way through.
Yeah, exactly.
Yeah, that's why the electrical engineers struggle in here.
Yeah, but you know, some people know about their outlets, and then some people.
We're gonna do.
Yes, that's. We gotta do like engineering, Mechie versus EEs, some cool project of some sort. All right, so you cut through all the holes now.
As per what I explained previously, I'm gonna do a selected faces. You pick the walls of the hole, so it has a reference for the axis of drilling for the drilling operation. So drilling operation for the holes that you can't afford to move around laterally in, and then I'm going to do a pocketing operation on the center hole. Now I'm going to do something different. I'm going to pick the top hole. Sometimes your contours are hard to access, either through like there's a construction plane across the middle or just some geometry in the way. All you need to do is select the right contour such that when you project it in the 2D plane, it's in the right spot. And then change your bottom height to stock bottom. And so now this pocketing operation will still go down to the bottom, even though I picked the contour around the top. But that pocket I want to do in multiple step downs. No stock to leave, multiple depths, 0.06. Let's see how that looks. That helix is wasting a lot of time. So I'm going to, helical ramping moves are great for aluminum in particular, just because even if your end mill is center cutting, that initial plunge into material can be a pretty shocking move from a physics standpoint. You're just basically engaging the entire area of the end mill all at once. So 2 degrees up to maybe 4 degrees is what you want to shoot for a helical ramp in aluminum. But for wood and softer materials, you can actually increase that angle to like 8 degrees. And so now you can see that that helical move is a lot faster. And furthermore, I'm going to adjust the starting height so that it starts much closer to where the part starts. So now we just have a little bit of that helix shape sticking out beyond the part. So let's see what we have so far. Select the entire setup, select simulate, show the stock, and just run through it.
And for those that haven't seen the simulate tool before, you could actually show them how they can see how long this entire thing should take. So that's another very useful factor of the simulation tool.
So in the statistics option, it's showing about 5 minutes, 6 minutes to cut this part. And I can also see that, hey, I forgot to do the outer contour. So you always simulate every now and then, just to sort of get your bearings, what's left to do. So I'm going to select 2D contour, pick that bottom contour around it. It's still defaulting to the 1/8 inch end mill, 40 inches per minute. I actually want 60. Passes, we're going to do 1/16 inch step downs, or 0.065, close enough. Even step downs, no stock to leave. It's got a little lead in, which I'll take it. The lead in is that little initial U shape. So when the end mill comes in, it's easing into the material, making contact slowly. Nice thing to have. And you'll notice this contour, it starts above where our model is. So it's wasting a couple seconds just following that pass. We don't need that, so we're going to start that toolpath. We don't want it to start calculating until it hits. I am breaking everything. We don't want our toolpath to start calculating until we reach this face. So I'm going to pick that face as my top height. You can see that that light blue plane moved down to match it. And so now the contour operation will start just a little lower, and we're not wasting time doing 2 passes in the air, basically.
Yeah.
So that brought that toolpath down below 1 minute. Can you also right-click each cut? Yes. So
yeah, you can. Yeah.
Over here, you go to machining time, and you can look up just that toolpath's statistics.
Yeah, that way if you see the whole thing's taking an hour and you got to see what got screwed up, you can kind of single out what looks to be the longest for some weird reason.
You know what's also taking an hour? This live stream.
Yeah, you see, I was on the money. I told people I prepped them. It's gonna take an hour. Winston, you just know so much.
That's a problem.
You got so much knowledge to share.
I think you're just slowing me down.
I like to keep the people happy. I like to communicate. You know.
You are too happy.
Anyways, now you're the one that's derailing this whole thing. We were almost there.
So if we simulate this entire thing real quick.
We're getting to witness our true relationship here.
So at the end of the day,
simulate.
Drill, come on. Bore out the center, cut around the outside. That's it. Some of the ways you could improve this, if you notice like lines around the outside or the outer surface not being perfectly smooth, is to run that contour with some stock to leave, about 0.01 inches, and then, like I said before, duplicate it, turn this into a finishing pass, just single pass, no multiple depths, no stock to leave, and it'll come around and clean up the outside. So initial rough contour, and then that little finishing contour that's just inside of it to clean up the walls. So if you're looking for ultimate precision and you're getting just like a little bit of rubbing or like lines horizontally across the part, or like you see a little U-shaped indent where the end mill is first going in, and that disturbance is sort of just digging into the part just a little more than you'd like, run that really light finishing pass at the end and that should clean it up. So the next Digital Fabrication Experiment podcast, we're looking to record early next week for release later next week. So hopefully within a week's time should be out, but no promises.
So for those of you there that don't know, Winston has his own podcast. And who's your co-host again
Uh,
for
Eddie Kramer of San Antonio.
Eddie Kramer?
He's
So if you guys haven't heard this podcast, it's actually extremely entertaining, extremely knowledgeable. I listened to it at lunch the other day, and it's just they were so kind of fluent throughout the entire thing that it's just easy to grasp all the information. So check that out if you guys haven't checked that out up to this point. You got another question?
Thanks for the plug, George. Maybe we'll have you on
I
sometime.
got you, my friend. I figured I'll save you from plugging yourself here.
Yeah, I suck at the whole business and self-promotion side of things. Should you use adaptive clearing instead? So adaptive clearing is good because it controls the lateral and axial cutting loads that your machine experiences by controlling how much you're digging into your part. So if we look at this pocketing operation, what does it look like? I'll look from the top down. Hopefully that shows. And as you cut, the entire cross-sectional area of your end mill is plunging into material at all times. When it comes around the next time, it's still basically just shoving the entire face of the end mill into fresh material. So in aluminum, that can be really stressful, and so a standard traditional 2D pocketing operation kind of sucks. If you're to do this with a 2D adaptive, I'm going to select that top face. I'm going to simulate that. We'll go more than one pass. About there's good. Top down, you can see that, hey, only a fraction of that end mill's cross-sectional area is engaging material. And sure, you could approximate that with a smaller step over in a traditional 2D pocketing toolpath, but there are some cases, like when your part isn't round and when you're going into corners, where where that small step over gets you less cutting load, it won't always work out that way. So adaptive, you're always engaging with, here it's about 40% of the end mill. I'm just going to make a really quick part to show you where 2D pocketing operations fail. So in corners, they don't work so well.
Where's your podcast located?
It is on anywhere where you get your podcasts, iTunes, Google Play, or Podbean. You can look us up on Instagram at DFX Podcasts. Yeah, we're there. You can find us.
I did not know you had an Instagram. I'm gonna.
Yeah, Did you look at my post? It was linked in there. I tagged the.
I don't read everything you put out there.
It'll be in the description. Relax there. All right,
I'm following it out here.
So I'm going to really quickly just throw in. So we've got an adaptive there, and I'm going to throw in a traditional pocketing operation with a step over of 0.05, roughly 40%. Let's see what my adaptive's optimal load is. It is also 0.05. So in most cases, that adaptive toolpath, that step over, and this pocketing are pretty close. So you would think that, oh, the cutting loads are going to be the same. But if you simulate the pocket operation, it's spiraling in stupidly. Man, it's going all the way down. All right, so this is the cutter moving through material. It's only engaging with 40% of the cutter's cross-sectional area. Then when it gets into the corner, all of a sudden, you've got this wide arc around its edge that is all of a sudden in contact with material. So the load, the strain on the spindle has suddenly gone from 40%, all of a sudden, it's basically doubled the contact area.
Yes.
And so your end mill is going to dig into the part a little more. You're going to get a little more deflection. It's going to want to kick out, push itself down, um, and actually it's going to push itself to the left if this is spinning clockwise. And so the loads are fluctuating wildly as you go through this corner. And that's with a traditional pocketing operation. In an adaptive, I'm going to skip ahead to after we start cutting. It is always, like at any given time, always using only 40% of that cross-sectional area. Even when we get into the corners, it is coming back and taking little nibbles such that the engagement's only 40%. And so that is where the adaptive really comes in handy. In aluminum, where your machine's pretty close to its performance envelope, the adaptive really makes it easier on the machine. But in wood, a comparable adaptive is going to take longer than a similar pocketing operation. So here I'm going to do pocketing operation, use basically a full step over versus an adaptive's. I need to use the same end mill for a good comparison. And let's say the optimal load is like 0.2. That actually came out okay. But there's a lot of cases where if you're doing an adaptive and you're doing a deeper cut but smaller optimal load, it's just easier to just go with a traditional pocketing operation. And the calculation time's lower.
Mm-hmm.
So it's, if you don't care about like the spindle load, if you're cutting a soft material, you can just get away with a regular 2D pocket. It's a little easier.
Yeah, it makes sense.
So that's all I really have for different approaches to machine the holes in this part. If anyone else has any questions as we wrap up, let me know.
Yeah, I'm happy that we saw a whole bunch of new faces out here today. That's pretty great.
So
here you go.
The problem with the adaptive is that depending on the geometry, you have a lot of time spent like over here in the corners. Your end mill is looping into the corner, following that curve, and then disengaging from the part. So it's actually almost spending like half the time not cutting. So I'm going to show you a different part that I was machining earlier today, where it's a really narrow part, and the adaptive toolpath just spent a lot of time not moving. I want the 1/8 inch. I think it was these pockets. So the adaptive clear for here, as it goes through its slotting, is spending a lot of time. Come on. The yellow parts of that toolpath are where it's disengaged from the part. So it's cutting, and then it's spending some time not cutting, moving to the next optimal position to start cutting again. And so for about half that time, it's actually not cutting. I'm using adaptive here because the depth of cut is really deep. Like we're talking like 5/8 of an inch. And the only way you can do that is by engaging a limited percentage of that cross-sectional area of the end mill. So I am trading the step over for depth of cut here. So adaptive isn't necessarily faster, but in this case, by allowing me to take that full depth of cut, it is faster. But for like large, flat 2D areas, especially if you can just use a dumb, regular 2D toolpath, sometimes it is faster to just not do adaptive. It's situational. You can try out both.
Yeah, I was gonna say you might as well just make both, simulate them you can see. It'll tell you.
Unless you have like a really complex part.
And then it can't. Yeah.
Yes. Um, I would, you know what? I'm just going to show
Move
you
speed.
the part for next week's video. Hopefully this weekend's video, if I can really get around to editing it. Um, of one place where I probably should have used a 2D pocket and not an adaptive, and that is the SpaceX Dragon bottle opener that I made.
Oh
Um,
man, this is cool. I gotta tell you, this.
yeah, this is turning into a big old show and tell. Um,
Well, yeah, people are interested. Um, Classic wants to know where you answer questions from your community.
Um, I'll usually answer questions if people ask them in like the Instagram comments for a post, but those are really hard to track. Like once it goes down in your
They're
feed, like
really
it
hard to track.
disappears
Yeah.
forever. Um, a lot of times it's just DMs or comments on my YouTube videos. But basically anywhere you want to ask is fair game. Um, I
Yeah,
should
I'm
just
pretty much the same way.
take a list of questions and do a Q&A or something on YouTube at some point. If I get enough volume of questions asked, then I might switch to a format like that. Um,
Yeah, I've seen a lot of people do like Twitter where they like just build up a whole bunch of questions and then do a live stream to answer them. That can work pretty well.
you can take out some of that transit time by increasing the move speed. So, man, this part is taking forever. The adaptive toolpath that I had here in this little organizer tray
Wow.
is it's called no engagement feed rate. I have mine set to 500 inches per minute, so my shape elbow is like flying when it's not actually cutting. But you need to change your gerbil settings to bump the limit up. It's set around by default to about 200 inches per minute, but the shape elbow can handle way more than that. So that'll be in the video of how I overrode that limit. Anyway, so this is the setup for my bottle opener Dragon space capsule. And the way it works is first operation, face the top, do an adaptive from the top to clear out most of the material, and then come in from each of the four sides to clean up the rest of the stock around it. Now, these tool paths are all adaptive, and there's a lot of linking moves and transitions as this thing cuts. So you actually spend a large amount of time waiting for the end mill to move back and forth. You can get around that by enabling both ways adaptive, but by default, the adaptive toolpath will move from like top to bottom, back off, move to the top, and then start cutting again. And with the Pocket NC's feed rates maxing out at 60 inches per minute, you spend a lot of time waiting for that movement. So in this case, I feel like I should have just done a 2D pocket. I'm only cutting this out of wood, so the loads are pretty manageable, and the toolpath would have looked a lot cleaner than this spaghetti. So it's situational. Use a little judgment where you think you need it, where you think you can get away without it, what's faster, and that's basically all I can say for when to use adaptive, when to use regular pocketing. So that's it. That's all I got. If anyone else has any questions, doesn't
That's
look
pretty
like
good,
it.
man. This is,
Oh wait, threading
pretty.
experiments on the Pocket NC. I have not yet, but I think Ed Kramer might have. If you check his Instagram, I think it's ekramer3 on Instagram. He's done a lot with the Pocket NC. He's been doing it for longer than I have by a couple weeks, and I think he's shown off machining mild steel on the Pocket NC, so he's definitely pushed the machine harder than I have. He has a more methodical approach to testing. So if you're curious about what it's capable of, I would check him out first, and at some point, I'll do thread milling on the Pocket NC. I just need the right project.
Get in there.
All right, well, I think we're good to
This has
go
been
for
great.
tonight.
I think.
I enjoyed
Thanks
it.
for tuning in, guys.
Hope everyone else did.
Happy to see a whole bunch of new faces. You what?
I
You
sure
enjoyed it?
had fun. Yeah.
Yeah.
Of course, I was just
This has been great.
rambling on, and no one stopped me. So now we're an hour and 10 minutes. But hopefully
Yeah, we'll
we
we'll we'll work on it, but you
yeah,
know, it
and
probably won't
hopefully
be
we
today, but we'll work
get
on
back
it.
into a regular routine because it's been like two
Yeah,
months since
maybe
our last live stream.
we've been busy, man. If
We
you
have been
guys
busy.
follow us
We've
on
also been
other
slacking.
medias, we've busy and slacking, kind of making that kind of combination. Why don't we aim for I don't know, like 3 weeks, 4 weeks from now,
Before the end of
we'll try to
July,
get another.
before the end of July, let's do another
Let's
one.
do that.
All right.
There will be another one before end of July. Keep your eyes out.
Sounds like a
I'll
plan,
invest
buddy.
in subscription model. All right. All right, guys. Thanks for tuning in. Catch you guys later.
Sounds good.